Right, let me just double check on your microphone. Right, you should be good to start.
Wow.
So can I start?
In the. In the 5 minutes.
Oh, 5 minutes, okay.
Yeah.
Okay, that's good.
15 minutes. Somehow get rid of all the stuff on the right. Is there a way? Because yeah, I should make your picture very conservative.
So let me see. So it's better? Oh no. Okay. Is it here? Okay. So,
The view, you go to the right.
okay, get it is. So what happens if some other people have questions?
Over there,
Okay.
Zhipeng, the right.
What?
In that screen.
Oh, that okay, that's another screen. Good.
I guess they're harder than taking. Because we know that. We could get the original something, but it's a trust. Do you know a simple group in the? Really? Oh, I wouldn't call it in our scale. No, it's okay. It's a good. It's a good. I agree that it's a big. Are you talking about? Oh, yeah. Maybe look at paper first or something. Yeah, paper first. Yeah. I guess like. Like a early first batch. Hi. Then. Students should be here. Here's some stuff. Direct. Okay. So, do the honors. All right, thank you everyone for coming today. You know, our seminars are continuing into May, but it's together, everyone's still here. Today we have Zhipeng Liu from the University of Kansas, and he'll tell us about the upper tail field of the KPZ fixed point. Please.
Yeah, thank you. And it's my great pleasure to be here, and I would be happy to discuss some of my recent results on the upper tail field of the KPZ fixed point. And this is a joint work with Ray Zhang, who is a postdoc at University of Utah. So this is him. I mean, most of the talk will be about the joint work with him. There are some other parts actually joint work with some other people I will mention. Okay. So there are like 4 parts of the talk. So first I will discuss some motivation of this whole story, and then I will discuss the main result of the talk. And we will move to the geodesic part. I will discuss some new result about geodesic related to the main result. And finally, I will give some kind of further questions which I don't understand. Okay. Okay. So let's start from the KPZ fixed point because everyone here is expert in this field. So I can skip a lot of pictures. So usually I give a talk, I will start with some random gross pictures stuff, but I can skip that part. So I just want to give some quick description. The KPZ fixed point basically is a space-time random field. This was constructed by Marditsky, Quaster, and Ramanik. This field is believed to be a universal space-time field limit of the KPZ universality class. And if we denote H KPZ xt, the KPZ fixed point, so here we assume T is non-negative, X is a real number. Then what is okay? So we call H x0 the initial condition, and especially in this talk we'll focus on one specific initial condition, which is called a narrow wedge initial condition. So what is a narrow wedge initial condition? So basically, a narrow wedge initial condition means we have one single support at 0. So H00 is 0, but Hx0 is negative infinity if x is non-zero. And this KPZ fixed point enjoys the well-known 1, 2, 3 scaling invariance. So basically, if we scale the space parameter by lambda 2/3, the time parameter by lambda, then we need to scale the head parameter by lambda 1/3. And they have the same law. And there are some other well-known marginals. For example, the one-point distribution. If we fix x and fix t, the one-point distribution of HKBZ actually is given by GUE trace equivalent distribution if we consider a narrow wedge initial condition. For other initial conditions, we can see other type of analogs of GUE trace equivalent distributions. And if we fix one time parameter, but we consider as a spatial process, then this process is called the Airy-2 process if we consider the narrow wedge initial condition, or some other Airy type processes if we consider other initial conditions. This talk will also be related to the geodesics, so I want to introduce briefly introduce the concept of Dirac landscape. So the Dirac landscape is you can view this as a random metric constructed by Davani, Altman, and Varag. This is also a universal limit of the KPZ universality class. I want to quickly discuss a little bit of the some property of the Dirac landscape. So if we define the Dirac landscape Ysxt to be the Dirac landscape with a starting point Ys and the ending point xt. So here we assume s less than t. Then for this Dirac landscape, there are some well-known results. For example, if we fix the 2 time to be 0 and 1, actually this is also called Airy sheet. So Airy y and x, these are 2 parameter random field. And we can also relate the Dirac landscape to the KPZ fixed point by the following formula. So basically, the KPZ fixed point is the same as the maximum of if we start from the initial curve, we plus the Dirac landscape from time 0 to the time t. Okay, so if we take the maximum of all possible y values, then they have the same law. especially because we want to restrict our discussion to the KPZ fixed point with a narrow wedge initial condition. So we have the simpler formula for this for the narrow wedge initial condition. So basically, HKBZ with a narrow wedge initial condition is the same as the Dirichlet landscape. We will start from 0, 0, because of our HY0, the initial data actually is 0. Only get one support is 0 at 0, and the negative infinity otherwise. Okay. And the Dirichlet landscape has a reverse triangle inequality. So basically, it means if we consider 3 different times from R to S, from S to T, then it turns out that the Dirichlet landscape from the point ZR to XT is always larger than or equal to the Dirichlet landscape from ZR to S plus the Dirichlet landscape from YS to XT. So this is always true. That's why, okay, that's why we see this metric, but this is not a regular triangle inequality, it's a reverse triangle inequality. Because of this, we can define the geodesic. This is also not a regular geodesic, but the reverse one. So from one point to another point. So on the geodesic, basically the inequality, the reverse triangle inequality becomes equality, okay, for any 3 points. Okay. So this geodesic, such a geodesic exists and is almost surely unique. In this talk, we will fix 2 points, 0, 0 and 0, 1. And we define the geodesic from 0, 0 to 0, 1 by pi t. So basically, actually, the geodesic is pi t and t. Okay, we have 2 parameters, but we define pi t to be a function starting from 0 and n at 0. And the time duration is from 0 to 1. And then we define the length, okay, along the length of the geodesic from the initial point to the to this point to be L of t. So this is a function between 0 and 1. So this is the Dirichlet landscape. Okay. So this it is a very natural question to consider the limited behaviors of the KPZ fixed point and the Dirichlet landscape, conditioning on a very large value at a fixed point. So this is called the upper tail conditioning. More explicitly, we can say, okay, so assume HKBZ 01 equal to L, where L is a large number, so L goes to infinity. We want to understand the limit behavior of the KPZ fixed point and also the Dirichlet landscape if we want to, with this conditioning. So there are many results. I would say many results in the about the large deviation in this upper tail region. For example, I just mentioned like 2 recent work by Davani and Varak in 2024. They studied the large deviation principle for the Dirichlet landscape, and Das Chai 2024 studied the large deviation principle for the parabolic array process. That's array 2 process minus a parabola, and the limited shape of the Dirichlet landscape under the upper tail conditioning. Yeah, there are. I missed a lot of results I think here, but yeah, I just mentioned 2. So the motivation result related to this talk is the following theory. So if we conditioning on a large value at 1, so basically means KPZ fixed point at the point 0, 1. Then what is known is that the geodesic from 0, 0 to 0, 1 will basically you can see it's almost a straight line. So it fluctuates of order L-1/4. So this, if you go from here to there, the width of this ridge is of order L-1/4. And the height will be a little bit larger. The order is L-1/4. The height fluctuates of order L-1/4. Moreover, one can study the Jordan law of the location and the height after rescaling. So after appropriate scaling, one can show that this is the Jordan law of the location of the geodesic, and the the lines, okay, I mean the head of the geodesic, they jointly converge to two standard Brownian, sorry, Gaussian random variables. So here we fix time t, okay, we fix time t. We fix any t, then the joint law of the geodesic location and the geodesic head actually they converge to independent Gaussians.
Know what the environment looks like from there?
What do you mean environment?
Oh, the spatial process.
I would discuss this a little bit later, but okay, so the spatial parameter. So if we zoom in that window, actually one should be able to see like linear decay. So we'll see something later. So inspired by this result, then one natural question is, okay, so we want to see what happens if we consider KPZ fixed point, what happens along this ridge, right? We want to zoom in this ridge. The ridge is of width L-1/4. So we want to zoom in this ridge and we want to see what happens of the KPZ fixed point along this ridge. Okay, this is a result by either Wang and myself. So what we have is that if we consider the KPZ fixed point along this ridge in the same scaling window, so you can see the space parameter is scaled by L-1/4, and the head function is scaled by L-1/4. So basically, if we do rescaling, one can show that this whole KPZ fixed point along this ridge converge to the difference of, okay, it's hard to explain. So it's kind of two Brownian bridges, but we have the absolute value here. So B2t minus the absolute value of B1t minus x. So I want to mention this. Originally, we did not read the form in this form. Actually, Bonint, I think, suggests we wrote in this form. So it's either to see because B1t is the argmax of this process. If you look at the right-hand side, B1t is argmax of the process. And B2t is the max of this process. So it's the argmax process and the max process. So there are two independent Brownian bridges. So this is a picture. If we really zoom in along the ridge, we should be able to see this picture. So it can also be written as a minimum of two Brownian motion with drift. But anyway, so this picture, you can see the location is like a Brownian bridge, but the head itself is also a Brownian bridge. Yeah, if you have questions, feel free to interrupt me. Okay. So after we get this result, we conjecture that, okay. So this is very easy to see. What we can see that you can see the KPZ fixed point at the maximum along this one. It has a Gaussian distribution. But on the other hand, so this, okay, so how to see that? The maximum process of the left-hand side actually converge to Gaussian. And from the previous slide, we can see the location, the head of the location of the geodesic also have the same distribution. Well, if you have two random variables, one is less than equal to another, and they have the same distribution, that means they should be equal. Okay, so I'm saying that heuristically they should be equal. So in other words, so this means the head LT should be the same of H, the KPZ fixed point. And at the same time, the pi t, because this is the location of the argmax, should match the argmax of this process. So based on this, one can conjecture the law of the law of the geodesic location and the geodesic head. If we consider as a process, this will converge to the law of two independent Brownian bridges. But I should mention that the first part of the conjecture actually was the first suggested by Basu and Ganguly in 2019. When I first obtained my result, I didn't realize their results. So I asked around, then they told me they studied, what did they study? They studied the last patch population model. They did not study the KPZ fixed point or direct landscape. They studied the last patch population model in the arbitrary conditioning. They were able to figure out the correct the exponent, the scaling exponent of the geodesic location, which exactly match our exponent like -1/4. But I think they didn't figure out the Gaussian part. So anyway, but they made a conjecture. They at the very end of the paper, they conjecture this should be the location of the geodesic should be a Brownian bridge. And this was later proved by Ganguly Head and Ninfu Zhang in 2023. They were able to show the first part, the geodesic location actually converged to the Brownian bridge in the arbitrary conditioning. But my understanding, the second part is still open. That's my understanding. So the height along the geodesic is still is also a Brownian bridge. I think this is still open. So that's the first part. So within the arbitrary condition, we can see, okay, so before the head point, we can see the Brownian bridge behavior. Then the next question, of course, the natural question is what happens after head point, right? Then this is, I mean, heuristically, this should be easy to understand, but this was first proved by Lisa and Zhang. Lisa is a PhD student at MIT right now, I think. Zhang is really Zhang. So they were able to show that after the peak point, of the head point, condition head point, then everything will come back to the KPZ fixed point again. So this is very natural and honestly, because if you have a very high point, right? So after that point, because this head point is a very rare event. So you expect the contribution will come from this point after this head point. So this was proved by them for a fixed x and a fixed t. But I don't think there's any difficulty to extend as a field limit. This should be true as well. Okay. So now I want to ask the main question of this talk. So we see two different behaviors in the same arbitrary conditioning. So one is the Brownian bridge, one is KPZ fixed point. So it's natural to ask, what's the crossover of the two limit behaviors? Okay. So what's the limit behavior? Near this peak point, we should be able to see some non-trivial limit field. Okay, so now we move to the second part. I want to introduce our main result. Yeah, both sides, yeah, before and after. So our main result considers two parts, okay. In principle, they are the same, but they are slightly different because we need to zoom in a very small window, okay. So we zoom in a very small window, we zoom in the space parameter by L-1, and the time parameter by L-3/2. And then the height, we zoom in by L-1/2. Then it turns out that if we condition on the KPZ fixed point at 0, 1 is larger than or equal to L, this will converge to some random field. So in the convergence is in the sense of convergence in finite dimensional distributions. And if we condition on HKPZ 0, 1 equal to L, then the same thing converge to a different random field in the sense of convergence of finite dimensional distributions. So this is different from the this is different from the previous result. In the previous result, there's no change if we replace this condition to another condition because they are like the scale is larger, so you cannot feel the difference. The main contribution comes from this equal to L. But if we really zoom in very smallly, zoom in the window very small, then even you increase a little bit of here, it will make some effect to the limit object. Okay. So there are a few remarks. So the HUT, okay, there are some story. Maybe I just discuss three first. So the reason we have two results, we first obtain the second result. We obtain the limit of the left-hand side, the joint distribution converges some function, but we were not able to prove this is a limited field. Okay, so we have a function, but we will not be able to show, okay, this function actually defines a limited field. So then later we came back to the first one. Then we were able to show the limit of first guy actually define a random field, because we have some kind of next probability argument to show that will actually define a limited field. Then, so this field, the first field is defined by its finite dimensional distributions, which we show this these distributions actually they are consistent family of distributions. Then they can by the Kolmogorov extension standard they define random field. So that's what we get. We don't have other property of this field. Then the second field is defined by the first field subtract the random variable at 0, 1. And HUT00 actually is exponential random variable with parameter 2. So we can explicit random distribution, which is easy to derive. I will show you in 1 minute. So, sorry.
Is it independent?
Independent of the second random field. I will show, yeah. So this is very easy to show that. So I want to show the argument. So everyone knows there is a arbiter estimate of GU traceable distribution. So it's given by this one. So basically it behaves like exponential function, exponential negative 4/3 times L3 halves. So this is a well-known arbiter estimate of the GU traceable distribution. If we change the head a little bit, if we consider this conditional probability, so you can see we fix time and fix 0, fix space and fix time. It can, because the intersection of these two events actually is the same as the previous event, because this is smaller. So it becomes the ratio of two tails, two upper tails. So if you can see the factor part this can converge to 1 when L goes to infinity. But the main contribution comes from the exponent part. Then you can see when you use the Taylor expansion for the second part, you will easily see you can get a non-trivial exponential distribution, which is roughly in negative 2h. So that's why we can see the exponential random variable for H00. Okay. Now the next part is about Jeremy's question. So we can prove this H0UT, the second random field, is independent of the exponential random variable. Independent. So they are totally independent. Okay, the next problem actually due to Davani. So when we first finished the paper, we sent the paper to Davani, and he told us actually one should expect when t equals 0, this field should be a two-sided Brownian bridge. And I was kind of surprised because I'm not working on the Gibbs problem. The Gibbs property area process. So we were able to check this using the formulas. So the formula is complicated, but if you let all the time equal 0, actually it's a Brownian bridge, two-sided Brownian motion minus 2 times absolute value of x. Okay, and I think the next property is a very interesting property. The arbiter field, this arbiter field, has kind of symmetry in the positive time and the negative time. It's very, for the 1-point distribution case, this is, I still don't understand why, but this is just from the formulas. From the formula, one can show the red, this is called the red tail of the arbiter so this is 1 minus the arbiter distribution at xt is almost the same as the 1 minus the the distributed function at x negative x negative t, yeah, minus at negative h. They have this differences. They have a factor of exponential function, dependent t and dependent h. This is very, I mean, this is a mystery to me at this moment. I still don't quite understand why this is true, but surprisingly, okay, if you combine the previous results, right, we should be able to show this result. If you let t equals 0 in the previous result, because we know HUT x0, the distribution, this is an exponential random variable plus a Gaussian random variable, right?
I see.
Yeah, so if we combine 3, 4, and 5, we should be able to see this guy. This is quite interesting. Actually, I was at the very beginning, I was curious why this is true. I mean, this is so simple. So what happens is, or if x is an exponential random variable with parameter 2, and z is a Gaussian random variable, then we have this simple identity. I mean, it's so simple that but I didn't see the identity before. And I try myself to prove it. I just took them 10 to 15 minutes to prove it. It's not that hard to prove it, but it took maybe 1 page long. It's not trivial either, but this is true. I'm not sure whether anyone else said this before or not, but this is kind of surprising.
The second best proof of this.
Yeah, you have a second proof?
You have the second best proof of this identity.
Oh yeah, yeah, that's right. So if you're interested, I think I have the, okay, I don't know how to show this. I don't want to share the screen. I have the proof actually. So let me see. I have the proof in a separate file, like 1.5 pages to prove this. I also tried to do some simulations, okay, but this unfortunately, I cannot put in the paper because this is not a real simulation because the formula is given by a series expansion. Well, I don't know how to simulate the high order terms. So if you consider series expansion, I only compute the first 2 terms. The third term will start with 1/3 factorial. I think maybe I have square. So that expected very small. So I just compute the first 2 terms. It turns out that, okay, if we consider density function of h0 ut at xt, we fix x equals 0, t equal to 1. So time 1, space is 0. The density function is the function above the first graph. You can see the red tail is very small, so it converges very nicely. It's similar to the red tail of the Tracy-Witten distribution. I can see, but okay. So what I can see that we can prove the right tail of the density. It is the sum of 2 terms. The first term is the exponential function part, because we didn't know there's one relation. We have the exponential part, right? We have the exponential function part. The second part is the same as the Tracy-Witten distribution, except for some constant difference. So the right tail, you can see it converges very nicely and very fast. But the left one, okay, it's hard to simulate. Okay, so I simulated a few pictures, but because it decays so slow and it takes oscillating terms, so the first 2 terms cannot really capture all the information of the density function. This is similar to the Tracy-Witten distribution, right? The left tail, the series expansion for the left tail does not really converges enough fast to get a picture. So the top graph is density function of fxt at when xt equals 0, 1. This guy, I said there's a table. The center graph is f0 negative 1. Oh. So you can see there's kind of symmetry. Okay. So one can show, okay, this is something I didn't write the paper, but this can derive from the paper. The density function at xt and the density function at x at a negative x negative t, they safe at this identity. So now it's easy to prove for the Gaussian. Okay, so if you put t equals 0, this is a density function for Gaussian plus x. This density for Gaussian plus h, plus x. This is a density function for Gaussian minus x. Then you can easily say, because like x plus h square minus x minus h square divided by x actually equal to h. So that's why you can see 2h. So this identity can easily be proved for t equals 0. Maybe within 1 minute, you can show this. Okay.
Isn't this thing symmetric in x minus x anyway?
I think you're right. I think you're right. So
So it's just the t minus.
yeah, if you replace, you move this part to the left, basically you still get the same identity. You just, so this is not necessary. So even t is less than 0, this is still true. So this is hold for arbitrary t. Okay. So now we want to see what's the relation between this result and the previous result we discussed before. We have the Brownian, if you remember, we have the Brownian bridge limit and we have the KPZ limit, right? So we can show that for this arbitrary field, if we consider negative time region, we zoom out this limit field a little bit, we can see the, okay, we can see the Brownian field. But there's a little bit difference. We are not able to see the Brownian bridge anymore. We can only see the Brownian motion. Because the window is so small, we start with, it lost information of the initial location. Remember, the Brownian bridge comes from the, if we come back to this picture, maybe this picture. If we zoom in the very end point here, it will lose information from here, actually. Like a Brownian bridge, you lost the initial location. You just have the Brownian motion. If we re-zoom in here, you just got the Brownian motion. So it's not surprising. So we will see Brownian motion inside Brownian bridge. Okay, so this in the negative time region, we can see this, we can recover the Brownian field. And I want to also emphasize that actually this result also is consistent with when t equals to 0. So what's this? Oh, sorry, no, this result is different. So this means actually this can also be seen from the Brownian bridge. If we zoom in the Brownian bridge field, if we rescale it properly, well, with the Brownian bridge, we zoom in at time 1 minus epsilon t, then this can actually converge to our Brownian motion limit. So because the Brownian bridge locally is Brownian motion, okay. And moreover, so this is a negative time region. In the positive time region, we are able to show this. If we zoom out, we are able to show that this guy actually converges to the KPZ fixed point with an average initial condition. So in other words, okay. So in other words, this random field interpolate the Brownian field and the KPZ fixed point. So it's kind of, I mean, I don't know, other field has similar problem, but this one field I feel like very interesting. It interpolate the Brownian motion and also the KPZ fixed point.
If I understood correctly, right, for the positive t, right, this is just an actual KPZ fixed point for the initial condition is this P0, right? Which is a two-sided Brownian motion, right? Two-sided Brownian motion plus an absolute value function, minus an absolute value.
Okay.
Because it's still, right, because the only conditioned up to this time, so afterwards it's still a Markov process. It's still a KPZ fixed point. So the only thing that changes is the initial condition every time.
That's right. That's right. I think that's sure.
So then you're switching that down to an arrow.
Yeah, I think you're right. I think you're right.
So that part we understand, but the other part is incredible. It's,
Okay. Yeah.
you can write it, you can relate the two distributions. It's amazing.
Yeah. Thank you. So basically, and these two results actually, they are consistent with the result when t equals 0. When we put t equals 0, because we know it's like two-sided Brownian motion, right? Two-sided Brownian motion. So if t equals 0 for the first result, if we do this scaling for the Brownian motion scaling, we can see we get this formula. We have a Brownian motion minus square root of lambda times x. We divide by square root of lambda. We let lambda goes to infinity. Then the only term survive when lambda goes to infinity will be negative the absolute value of x. Yeah, this is exactly the same as the b2 minus b1 minus x. but we put B2, B1 equals 0. And moreover, in the positive case, we put T equals 0, then it becomes, this becomes 1/3 scaling. Then you can see this quantity will become negative infinity because this guy is too large when x is non-zero. This guy is too big. So this will converge to negative infinity when x is non-zero. But when x equals 0, everything is 0. So we recover the KPZ fixed point, the initial condition of the KPZ fixed point. Okay. There are a few further remarks. I don't guarantee they are correct, but I believe they are correct. Okay. So we believe that this Arbuthnot field is a universal field in the KPZ universal class of the Arbuthnot conditioning, because
it doesn't matter what we start.
there are a few meanings. Okay, so it doesn't depend on the model, because for every model you converge to KPZ fixed point, right? So at least for some region, they should converge to this limit. The second case is, okay, we believe that this even in the periodic KPZ fixed point, because you forget a lot of information, right? So it's a local behavior, it's not the global behavior. So it should be, at least as long the periodic does not shrink too crazily, yeah, we should be able to recover this Arbuthnot field. And they will also believe that Arbuthnot field does not depend on the initial condition. If we start from a different initial condition, as long as we have nice control, then we would be able to get the same limit field on the Arbuthnot conditioning. So it's easy to verify this for the flat initial condition, because this we had the result. Okay, I want to mention the flat initial condition. Okay, what happens? For the flat initial condition, everything the limit field was also obtained. For the KPZ fixed point with flat initial condition with the Arbuthnot conditioning, the limit field is also obtained. The only difference is that this is B2t minus B1t minus x minus a linear term, which is a linear function of Gaussian random variable. Then this linear term, when we take epsilon equals 0, because we have epsilon times some random variable here, right? Epsilon divided by epsilon negative 1/2 will still converge to 0. So in other words, if we zoom in that random field, we'll get the same limit here. So that is a very strong indication that even we consider different initial condition, the initial condition information will be lost when we consider Arbuthnot region. So if you have a linear term here, linear dependent on epsilon, then this will not appear in the limit. So that means this is a strong indication that this guy is the same with other initial conditions. Okay. So I think with how many minutes do I have? Maybe 12 minutes or 10 minutes? 10 minutes. Okay. So I will skip a lot of things. But anyway, I want to discuss one main ingredient of the proof, which is of independent interest. So basically, the main ingredient of the proof is the multi-point Arbuthnot estimate of the KPZ fixed point. So what's the meaning? So it means if we consider, okay, so when we already know the 1-point Arbuthnot distribution, 1-point Arbuthnot approximation of the KPZ fixed point. If we consider a bunch of points near this point, and if the large parameter is almost the same, then we should expect in terms of leading order, they should be the same, right? So the multi-point Arbuthnot estimate should be the same as the 1-point Arbuthnot estimate, except for the order 1 term. The order 1 term is a function, is a non-trivial function. So this is one main ingredient of the proof. So what we prove is that, okay, if we consider a couple points near 0, 1, conditioning, consider the joint distribution, that they all larger than equal to some kind of L plus some order L negative 1/2 term, then they are almost the same as the 1 point in the leading order, 1 point upper estimate, but they differ as some kind of order 1 function. And this is the main ingredient, the ingredient of the proof. And this function is non-trivial. But when m equal to 1, this actually is this function. Okay. So I still have like 10 minutes. I want to discuss a related result about geodesic. So as we discussed before, so if you we went through the story, right? We start from the geodesic, then we go to KPZ fixed point. So now we fully understand KPZ fixed point. So now we want to come back to geodesic. So the geodesic is very close to the information of KPZ fixed point. So we can zoom in the same window near the head point. And we want to understand what the geodesic behave, or what the distribution of the geodesic location. The geodesic should behave the same order. Okay, the height also behave the same order. So what do we get? Okay, so this is something in progress with Chen Ma is my student, and Tejasvi Tripasi is a PhD student at Michigan, so he will be a postdoc in Kansas. So what we can show is that the geodesic location and the length from the initial location to this one, they fluctuate of order L-1 and L-1/2 if the time window is of L-3/2. They will converge to this guy, this function. Okay. I cannot claim too much at the moment because we haven't finished yet. So what I can say, okay, P is a non-negative function. We cannot even claim the density function is a John density function. We haven't proved that yet, but I believe this is true, and we are in progress to prove this. So we have an explicit formula for this guy. And moreover, if we zoom out, as what we did for the KPZ fixed point, if we zoom out, we get the product two Gaussian densities. But the variance, but we also will lost the information of the initial location. So you can see the variance is t, right? So it's t here. It's not t times 1 minus t. Okay. So this is something in progress. And from this formula, you can see this p should be non-trivial. But we are still, we didn't prove this actually is a John density function yet. We need to work on that. And I don't think I want to discuss the formula. And okay, so maybe a few. I think I already mentioned this property. So the right-hand side actually is a John density of two independent Gaussian variables with variance t. Okay, basically both are t. If we but the T of is just a different parameters, different constant term. And we lost some information of the Brown bridges of the geodesic in the larger scale. Yeah, so because what we expecting if the in the larger scale is t times 1 minus t, this is reasonable because we lost information of the starting location, and we expect this is a John density function. So I want to convince you in like one picture. Okay, so this is a graph. Okay, so so from the graph you can see this is John density function, but unfortunately, okay, I cannot claim this is the correct graph. So the right-hand side, so the John density function is given by a sum of, is a series expansion. When starting from the third term, there's a factor in front is at 1/3 factorial square. So we expect the third term will be super small. So we just compute the first two terms. And this graph comes from, we use a Python code to compute the first two terms. We use a very precise Python code. It's very, very slow. Like 1 hour, you can get five data points, something like this. So we split this to many different small domains. We compute the value of these small domains. Each domain represents 9 points. So then we patch this up. We get a picture like this. You can from the picture you can see it's non-Gaussian. At least from the picture, you can see this one is 2, this one is 3. This side is smaller than that side. Okay. And but if we, I don't know, yeah. So this is something we are still. So we can rotate the graph. Actually, it needs not very symmetric. The difference, okay, that's what I mentioned. So there are some fancy method which basically drop the preciseness. So if we don't require this so precise, maybe I forgot the method. It's kind of you can okay. So there are some fancy method. We use ChatGPT help. I've got help from ChatGPT. So we are able to produce the data at a much faster speed, but less precise. So they're almost the same, but they are like the difference is that 0.001, something like this. I mean, but we cannot claim this a picture. We just say, okay, this roughness. So this guy is a less precise picture, but the purpose I use the same size, same window because I want to see the difference is very small. They are basically the same picture. But we can, because this is so fast, so we can run at any window actually. So,
What is the coloring?
this coloring, so basically make you distinguish they are different small domains. So you can see.
How much you have to iterate your algorithm?
Sorry, what?
How far you have to what precision you have to iterate your algorithm in the region instead of the color?
No. So just basically, I think that basically we just do we just okay. So we just run for each small domain. We run for 9 points. Then we just glue all the data and then get a picture. And these different colors to distinguish them. Okay, so you can see. Okay, this is a patched picture. This is another one-time picture. And this is a more maybe look better. So this is a faster algorithm, but less precise. We can see, you can see almost equals 0 here, -4, almost equals 0 here. Here you can see, I mean, because what we got from Python, you get a 3D picture, so we can rotate it. We can see it doesn't look like Gaussian. That's what I'm saying. I'm trying to say.
In fact, what you should do is draw some level sets.
Oh, that's a good idea.
Because, for Gaussian, there are ellipses, and they can tell ellipse by eye.
Yeah, but I'm not sure whether we can see. Yeah, maybe. Yeah. Yeah, but okay. So this is a good question. I mean, we from the formula, we definitely we can see it should not be Gaussian because we have cubic exponent, right? But but theoretically, we cannot really prove this is not Gaussian. Yeah. Okay, something interesting. Yeah.
Because it's a sum.
But what I can see that the limit of this guy is not Gaussian. Yeah.
Yeah, I think you know that the tail and you know that the tail and X is going to be cubic.
Wouldn't you say the limit's not Gaussian?
I mean the limit is Gaussian, so that would say.
But
But the Gaussian limit is still Gaussian, right? So
the P you can check, like the P is going to have some cubic tails.
Yeah.
So the P is not.
yeah, this is something we are in progress. I just want to show some partial results. So we have these pictures, and we need to show this actually. Okay, so we need to show this actually is a John density function, and we also need to show that this is non-Gaussian. Okay, so we have the exact formula. It might be trivial, right? Maybe this equals 0 if we choose the wrong window.
Oh.
Right, so we want to show, yeah, we can show this is non-negative, but we cannot show this is non-zero. So that's this is the reason we need to show. I mean, from the picture it's trivial, but yeah, but mathematically to show this non-zero is non-trivial. Okay, I think okay, we have 1 minute. I want to quickly discuss some further questions. Okay, so as I mentioned, we expect the upper field is kind of universal. You have some universal. So one question, okay. Is it possible to show the same field for the other models or other initial conditions or in other domain and so on? And also the analogous lower tail, this is a very difficult problem because lower tail, at least for our formula, is not suitable because it's like a series expansion diverges actually when in the left tail region. So it would be nice to see similar result for right tail. And one last question is that, as we mentioned, in the global scale, the argmax should match with the geodesic location. But what happens in the smaller region, smaller size? Do they still match? This is something I'm curious, but I don't know. So is it still the same, the argmax of the upper tail field match the geodesic location. Yeah,
The lower tail, you expect something very different.
that's right. Lower tail, we should expect something different, quite different. So, yeah, but this is a very interesting question. Yeah, I think that's all for today. Thank you. Questions?
Do you have any guesses for the lower tail? Like, so would it be like a straight line, or what would it be instead of a brown thread? Do you have any guesses at all?
I don't have any guess, but I definitely know some. There are some papers, physics papers. I think probably maybe okay. Even math paper, maybe Li Chunchai did some work. Correct, Jeremy, is it correct? Li Chunchai did some lower tail. Maybe Li Chunchai with Leidocell. Maybe they have some similar some kind of large deviation result, I guess. But I didn't look at the details because I don't know, because I'm interested in the fluctuation level limit, but it seems that I don't have a tool to access the problem. But I'm not sure. But is there a way like either Riemann-Hebel method to do that? I don't know, but it might be very difficult. Yeah.
It's much harder to do lower tail conditioning.
Yeah, that's right. So I say from the formula, it's very hard because the formula you can expect is similar to like treat with the distribution, right? If you use a series equation of the Fredholm determinant, it's easy to do right tail because the main contribution from the first term, but it's harder to do the lower tail because every term makes the contributions, and I think the series diverges, right? Horrible.
Does this exponential trick that we have between the later times and lower times switch the two tails? Is it plus h to minus h or something?
Okay, this is a very good question. You're right. For this arbitral field, for this guy, right? So you can see the lower tail for the arbitral field actually is the same as the arbitral for the arbitral field in the positive time region.
Yeah.
But then this side is hard. So basically, it's just a flavor.
I think you can say everything you want about the positive T thing, really everything, because we understand. Let's just keep this explained from this funny initial condition. Okay, so you can. So there is a lot you can understand a lot. So you could just then transfer to this one by this formula.
Yeah, but you know, okay. So in mathematics, the difficulty is the same. So we have some kind of series expansion. There's one side that is easy, the contribution from the first few terms, and there's another side which is difficult. The series doesn't converge. So if the
We could use expansion around the upper tail, so this doesn't survive.
Now, this is an exact formula. This is a density.
yeah, the density. Yeah.
So if you want to understand this HUXT, and if you understand the density for positive T in any regime, then you will understand the density for negative T for any regime. And for positive T, it is just a KPZ fixed point started from this kind of random wedge. Okay, this is fine.
Yeah.
You want to understand the lower tail of the field.
Yeah. So that you can see. Oh, that's good. This
So-
is just the KPZ looks like there's a one initial condition, so you can do that.
But this is still an upper tail problem.
Yeah. Understanding the lower tail of the positive. I think
So-
I think you do get something more.
Yeah, sure.
But I think you
But
might,
it's possible.
but I think you might get like,
What I'm saying is an ordinary computation and vector landscape. We're not studying some very complicated, something that you only have access to for.
yeah, I think when you look at like in this case, in the upper tail field, when you look at the lower tail of the upper tail field,
Yeah.
it'll be dominated by the lower tail of the two-sided Brownian initial conditions. Whereas the upper, because that gives you the x squared. And so that's what's gonna dominate the lower tail.
Well,
And then when you go to the-
it won't go anything, because you still have a narrow wedge. So that you can't go below that. It's greater than or equal to the narrow wedge initial condition. Because it's something that's centered, its value is 0 and 0. Like it's two-sided.
And so this, what's the, is T? Okay, so this, okay, yeah, so the sign of T. So this allows you to probe the lower tail of the KPZ fixed point from this two-sided round.
So one thing I can think about,
You could go that way.
one thing I can think about is for the first formula, you can always get a bound of this guy because the probability is always less than or equal to 1. That's what I can see. So you can get a trivial bound by exponential function. So for example, the left-hand side, for any edge, we're always bounded by this function, exponential -2/3 t times minus 2h. Because the right-hand side, because this is a probability, right? It's always less than or equal to 1. But this is some kind of trivial, I don't know.
I wonder, Ben, let us look at, to me, this reminds me a little bit of these formulas that you guys use. You know, like this kind of identity between.
I mean, it's the moment generating function. Like that's at the moment generating function.
Yeah.
This is the same.
Does it look familiar?
I had no. I mean, so because that one's like it's that one is about it's just so it's for the height function with like special initial with like sort of half stationary initial data. That's where your other parameter is. I don't know if that is here. So those formulas is like you have instead of stationary initial data, like stationary initial data always has some parameter, like so you take and then you just take like kind of step.
Yes, that's exactly what this is.
Here.
Yes. One of them is exactly the station. Two Brownian motions, right? It's the limit of this. Well, any students?
Also, what you were saying before, so if you look at the lower tail of this, so, I mean, you can't, are you saying you can probe the lower tail and you need to explain, so after time 1, you're exactly you need to explain, but you do the lower tail of this upper tail thing, and then you can do this time reversal.
To get the upper tail of the previous.
Yeah, exactly, which is, I think, probably pretty simple. So this, does this give you a way to get the lower tail of KPZ fixed point, like, surely, no, right, or something, I assume.
Yeah, should be something.
Okay.
But I think my feeling is that this exponential guy was gonna get out of the way pretty quickly, and we just gonna get the trace we don't know.
Yeah.
And that's my guess. But they might be wrong. It's only like the next terms that this
Yeah.
exponential will even matter.
Right.
Yeah, I think it's like
It's easy for that to be small, right? But it cannot be smaller than the narrow way. So it will be like the lower tail instead of the narrow. And then the traces of that. That's it. I think you're wrong. Okay, well, thank you.
Thank you.